Let's talk about how the internet works. Look at what is the internet, what is the internet protocol, and what is internetworking. So we'll introduce some concepts today. Tomorrow maybe look at some of the details and look at addresses, and maybe some examples next week. First, we need to talk about what's the motivation for this thing called internetworking, and then we'll explain what we mean by internetworking. Then we'll look at an example of an internetworking protocol called the Internet Protocol, and look at specifically spend some time looking at IP addresses. What you know so far, last week we talked about local area networks, LANs. We use LANs inside our home, inside our offices, inside our buildings. And we went through some different types of topologies, different medium access control protocols, different technologies. And we went through one example standard, 802.3, the Ethernet LAN standard. So in LANs there are different types, and some companies may choose one type over another one. That is, you set up your own LAN at home, you may use a different technology than what you use inside a company or an organisation like SIT. So they have different purposes, depending on your requirements. Most of the LANs cover a relatively small distance, small area, tens of metres, hundreds of metres in some cases. Operate at layers 1 and 2, the physical layer and data link layer. In some cases we can connect one LAN to another. That is, we build a LAN using a star topology and another LAN, and we can connect them together to make a larger local area network. The other thing that we've mentioned is, and all through the course, is wide area networks. LANs for connecting across a small area, wide area networks connecting across a larger distance. In particular, to interconnect LANs together. So to connect one LAN at this campus to the LAN at our Rangsit campus, because we want to communicate, we can use a wide area network connection between the two campuses to cover a larger distance. And again, there are different technologies available for wide area networks. Some use point-to-point links, and some use an entire network. If this cloud represents our LAN on this campus, and this cloud represents the LAN on the Rangsit campus, and we want to connect them together, we could have a single cable, or in fact what we actually do have, not a cable but a wireless link. We have a special device and we have a tower on the top of our other building and a wireless link which is a point-to-point link, the way that we use directional antennas between our two campuses. So our wireless link across that 10 to 15 kilometres is an example of a point-to-point wide area network link. There's just two endpoints, two devices attached to it. They connect our two LANs together. That's one example of a wide area network. Of course, an alternative, instead of using the wireless, we could connect to some internet service provider or some telecommunications company. And they may have their own network that connects across Bangkok, for example, made up of their own links. Maybe they're wireless links, wired links, optical fibre, different technologies inside here, which becomes a wide area network across the city. So this is an internet service provider. So it may be a packet switch network, for example. And it may cover a large area. An example packet switch network, where these are the packet switches. And then we would connect our LAN at the Rangsit campus to their wide area network. So wide area networks may use point-to-point links or an entire network using packet switching or circuit switching. The devices that connect the two together need to support both technologies. This device here that connects our LAN to the wide area network needs to support the technology used on this network and the technology used on this network. Same as this device, it needs to support wireless transmission for our wide area network link and also, say, Ethernet for the LAN connectivity. So that we know about LANs and wide area networks, and organisations throughout the world may choose different technologies depending upon their requirements. Someone may choose a wireless link, someone may use a different wide area network technology, and same within the LANs. What we would like is to allow any computer so any end user device to communicate with any other end user device. Independent, and this is an important point, independent of what LAN or wide area network technology they use. So if we have a computer here which is connected via Ethernet, and we had another LAN here, some other organisation, or it may be on the other side of the world, and another computer connected via even a Bluetooth link to some other device, a Bluetooth wireless link, then ideally we should allow this computer to communicate with this computer, irrespective of what technologies they use to connect to their local area network, irrespective of what technology is used in here. We don't care that this is wireless, this is a packet switch network, a circuit switch network. From the end user's perspective, we just want to be able to communicate with anyone. And that's the role of Internetworking. Connect the LANs and WANs together to Internetwork. These are separate networks. Internetworking is about connecting those separate networks together, having more than two networks. And by connecting them together and allowing anyone to send data to anyone on any other LAN, we achieve our aim of communicating with anyone. So that's the concept of Internetworking, connecting LANs and wide area networks together, irrespective of the technology that individual networks use. Some of the things we need to achieve this. First, some terminology. The devices that connect our local and wide area networks together are called routers. They're the names of the devices that connect our individual networks together. So in this example, we just have clouds representing individual networks, and they're connected together via these devices, and they all represent routers. So a router connects one network to another network. Two more LANs or WANs together. So this one connects two networks together. Do we have another? This router connects three networks together. So in general, two or more networks are connected via a router. Routers are packet switches. So we know how packet switching works. We send a packet to the router, to the packet switch. It looks at it, looks at its routing table and determines to send it onto a next packet switch, and to the next one, to the next one, to the next one, until we reach the destination. So we use the concept of packet switching. And routers operate at the network layer. So we're now up to the third layer in our stack. Physical layer, data link layer, we're now at the network layer, layer 3. Some other terminology that we use or we're going to use. So we have the individual networks connected together via routers, and together we get one large network. So we've got a network, one network made up of many networks. To distinguish them, we often call these individual networks subnetworks. So this is one subnetwork, this is another subnetwork, a subnet for short. So in this example we have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9 subnets, 9 subnetworks. And we can call the entire network an internet. It's a network made up of interconnecting other networks, an internet. So this, on the next slide, we have subnet networks, which are the individual networks. Internetworking is the concept of connecting those subnets together. An internetwork, or for short, an internet, is the resulting network. So we have one internet here, and we have our 9 subnets that create that internet. The internet with the uppercase I, an internet we refer to any network made up of connecting subnetworks together. The internet is a specific internet that uses the internet protocol, which we're going to go through in this topic. And it's the network that we use today. You can build your own small internet without attaching it to the larger internet. I can take 2 computers, or I can a set of computers, put them in my office and create my own small internet inside that office without connecting to the outside world. So we sometimes distinguish between a general internet, any network made up of connecting subnetworks together, and the internet with an uppercase I is a specific network. Some other concepts that we already know, in fact. Routing is the process of discovering what is the best path from some source to some destination. Remember, these are LANs. There are stations attached to them. End user devices are attached here, although not shown. They're connected to this LAN, and same with the other LANs. So routing is about finding a path from one node to a destination node. Forwarding is about sending the data across that path, to forward that packet, that data between the packet switches. We know what packet switching and circuit switching are. In the Internetworking, the routers are in fact packet switches. What else? A packet switch at the network layer we'll call a router. It's the same thing, but it's just we just commonly refer to as a router. We saw last week we also have switches in our LANs. We'll try to refer that as an Ethernet switch. We saw last week this example, and we had another example of a switch. You see that there are, for a switch, from last week we connect our N stations to a switch, all via a single cable. There are 4 ports on this switch. Last week we also had an 8-port switch. We see this has a 5th port as well. This device is both a switch and a router. That is, it connects the 5th port to the 4 ports. We can have our 4 computers on our LAN attached to the 4 ports for the switch. Here's our device here. And the 5th port can connect out to another network, whatever that other network is. In this example, or in this device, it's another Ethernet network. in your home, maybe ADSL modem / router, if you've got ADSL at home, you probably have something similar to this. Some of you will have a port where you plug your telephone line into, and some other ports to plug your computers into. That's also a router. That connects your local network to the wide area network, the telephone network, and then onto the internet. So this is an example of a router, a very simple example of a router. I cannot give more realistic or larger examples because they are too hard to carry. So we know what internetworking is. We need to understand what a protocol needs to do to support internetworking. What do we need to make it work successfully? So we need some protocol to allow us to deliver data across these different subnets. They are different subnets, they use different technologies, but we want to be able to communicate across any of them, irrespective of what technology they use. And we use an internetworking protocol to do that. What does an internetworking protocol in general need to do? It needs to provide links between the individual subnetworks. So a router, like this router, will connect two networks together. One interface to provide a link to one network, and this one we have four interfaces to connect to one other network. So a router has links to two, usually two or more different subnetworks. An internetworking protocol needs to provide some routing mechanism and some forwarding mechanism to deliver data across the network. We've covered routing and forwarding already when we looked at packet switch networks and when we look at routing after that. Often we'd like to keep track of the use of a network. In which example? In this example, if I send data from my local network here to someone on the other side of the world, and if it goes through this wide area network, the owner of this network would like to keep track of who is using it, who is sending their data through it, so maybe they can charge some money to use this network. And also, if there are errors, something goes wrong, we'd often like to report the status of what's happening so we understand where the errors are. So we often need some way to keep track of the use of the networks and to provide some status information. These are things that some internet working protocols need to do. And perhaps most importantly, an internet working protocol needs to support the fact that the different subnets use different technologies and have different design decisions made. Some of the differences which we'll go through, for example, addressing schemes. Two subnets in our internet work, our internet here, this subnet and this subnet, will use two different technologies potentially. To allow data to be sent across both of those networks, we need to support or handle the differences between them. Let's use addresses as the first example. Just concentrate on two parts. LAN 1 is connected via router to wide area network 1. Just these two subnets. And actually we'll go up to LAN 2 as well. Let's say we have a host or we have a station attached to this LAN. So when I draw a cloud now, I mean any type of network. It could be a star topology in here, a bus topology, a point-to-point link. I don't care at this level of detail. I'm just saying that there are stations, there are computing devices somehow attached to this network, and there's a router attached to it. So here's one station, and we have another one here that we want to communicate with. This network is using technology A. This is using technology B and C. For example, this may be Ethernet, this may be a WiMAX link, and this could be a token ring network. They may use different technologies. We want to communicate from this computer to this computer. Normally, or in general, each technology will have its own address format. The stations on this network will all use the same address format. For example, this station may have address A1, and this router would have address, instead of, let's just call it A, and this one B. So this is the address of this station and the address of the router. They need to be different if they're on the same LAN, and they need to be in the same format. And the format in this very simple example is letters. We've seen an example of a format last week where we saw the 48-bit addresses of IEEE addresses. This is just a simplified example. Instead of 48 bits, I say we've got one of 26 values, a letter, to identify a device. So these two devices can communicate with each other. Maybe they have a direct link between them. If A wants to send to B, it creates some frame and transmits it across that link, and the destination is B. A understands the format of the frames that it sends to B and the address format of the destination. It has some software and hardware that implements the protocol to communicate between those two devices. Over on this LAN, maybe on the other side of the world, we may use a different format for addresses. Maybe they're numbers, number 1, and here number 2. And they connect together. So they can communicate within the LAN. But our problem is we want to allow A to communicate to 1. The devices are using different formats of addresses. You can think that they only understand their own format. So there's no way for A to send a message to this device because it doesn't even know the address format used by this device. There are many other problems as well. So you can think it doesn't understand the format used by that device. It's as if they use two different languages. Here we use one language, here we use a different language. We cannot communicate between this device and this device because they use incompatible languages. So we need to handle that somehow. And in fact, we'll see the way that we do that is that we give the devices an additional address. Let's say this one has an address of A, and let's give it another address, which let's use lowercase letters combined with a number. This one has the address uppercase A, and we give it a new address, A1. The format here is a lowercase letter followed by a number. And we give this computer an address using the same format, but different. Let's call it B3. Same format address, and by doing that, we've at least solved the problem that, okay, now we can send a message and we can at least know the format of the address of the destination. Because of the differences in the technologies of the individual subnets, an Internetworking protocol needs to handle those somehow so that we can communicate across different subnets. Another case of the differences between subnets. Just one more example. There's some listed here. Different subnets use different addressing schemes. Different maximum packet size. We've said that some protocols may limit the size of data that they can send. We need to deal with that. If this network allows us to send 1,500 bytes, That's the maximum amount of data to send in one frame. This network may limit to just 500 bytes. So we could send one frame to here with 1,500 bytes, but then we'd need to break it into 3 frames because this one only supports a maximum of 500 bytes. So we need to handle those differences within the different subnets. We'll see some more specific examples of how to deal with that later. Error recovery. This network may support retransmissions. That is, if I send data and I don't receive an acknowledgement, retransmit until it's successful. So it provides some error recovery across this network. This one may not. Maybe it's a very simple protocol and it says send the data, if it gets there good, if not, do not retransmit. Or maybe it uses a checksum to do forward error correction. Maybe this uses stop and wait, this uses selective reject. So they may use different types of error recovery, some no error recovery. And we need to deal with that across the entire internet, from source to destination. They may use different ways to report the status of the network, different mechanisms for security, and other differences between the individual subnets. An internetworking protocol should accommodate all these differences so that we can still communicate from here to here. Even if they are different in the subnets, we still want to be able to communicate. One example of an internetworking protocol is called the Internet Protocol. So that's a specific protocol. It meets some of these requirements that we've listed here. Not all of them, only some of them. It turns out it's the most popular internetworking protocol now and is used by almost all devices. So that's what we're going to cover. It meets some of the requirements that we need for internetworking to work. The ones that it does not meet are handled by other protocols. 2 of them that specifically are ICMP and TCP. We'll cover TCP in the next topic. So what we're going to do for the rest of this topic is go through how IP works, the Internet Protocol. So we want to connect LANs and WANs together. We do so using routers. Routers use packet switching, and we're going to use the Internet Protocol to support the delivery of data from source across multiple subnets to a destination. Let's look at what the Internet Protocol does, or IP for short. There are different variations or versions of the Internet Protocol. We're going to focus on the most commonly used version today, IP version 4. IPv6, IP version 6 is available and is in use in some networks, but not widespread use. Maybe in the future, next 5-10 years, it will be in widespread use. So we're not going to cover the details of IPv6, just the most common one. There are other internetworking protocols. In the past, Novell created different network technologies, and one of them was called IPX. I think Apple had its own internetworking protocol. X25 is another example. So there are other old ones, but no longer in widespread use. You can think that the Internet Protocol has won and is the most commonly used of these different internetworking protocols. IP developed in the US maybe 30 to 40 years ago, and has become what's called an internet standard produced by the Internet Engineering Task Force, the IETF. Just another organisation that creates standards. We saw last week IEEE create some standards. IETF creates different types of standards related to the internet. IP, what does it do? It's a connectionless protocol. We'll explain that, but basically we do not set up a connection. We saw when we talked about different types of switching this concept of setting up a connection or a circuit. IP does not have a concept of a connection. It operates at the network layer, it does internetworking, and it uses datagram packet switching. So we know how datagram packet switching works. We just take our packet, use our routing tables to say send it to the next packet switch, that sends to the next packet switch until we get to the destination. In our case, those packet switches are routers, or we call them routers, or IP routers. So it provides data delivery. We have a packet or some data at the source. It will try to send it through to the destination. It provides formats for addresses. We just gave an example here. Because the different subnet technologies may use different types of addresses, to overcome that, we give a new type of address to the end stations. In fact, also to the routers, we'll see. And these are called IP addresses. These blue ones, we'll see there's a specific format, they're IP addresses. Well, these are not IP addresses, but we'll go through the format of IP addresses. So the Internet Protocol defines what type of addresses to use in the Internet. Data delivery, addressing, and fragmentation and reassembly, which is if we have a packet that's too large to be sent across a network, here if we had a packet of 1,500 bytes, and we need to send it across a subnet that supports just 500 bytes, we need to fragment that packet, break it into smaller chunks, and then eventually reassemble it back together again at some point. So IP does that for us. And that's all. IP is relatively simple compared to many other protocols. Some things it does not do. It does not have any concept of a connection. It's connectionless, means we do not set up a connection. We do not control a connection. IP does not do error control. There is no concept of retransmissions. If we send some data, there's no acknowledgement coming back in IP. There's no concept of flow control. If we send some data and it overflows the receiver is not going to tell the source to slow down. IP does not do that. Because IP does not do that, does not provide these features, but sometimes we need them, there's another protocol that does it for us, TCP. So we'll cover that later. IP does not do status reporting. It doesn't report errors in the network. There's another protocol that does that for us, ICMP. IP does not provide any priority to data. I want to send my data across the internet, and you want to send your data across the internet. I'd like my data to give priority because I'm a faculty member here, you're just students. We cannot do that with IP. Everything is treated the same. There are other mechanisms to provide such a priority service. And it provides no built-in security. Again, there's another protocol called IPsec that provides security. So in fact, it's very simple. And that's one of its advantages. Because it's simple, it can be used in many different locations or many different devices. It's easy to implement, and it's become widespread. Its use has become widespread. This places IP within our 5-layer stack, physical layer up to application layer. Just using some example protocols in each of those layers. We see IP is at the network layer in the center. Below that are different protocols used in LANs and wide area networks. We've seen some, the IEEE 802 standards. There are others that we've either mentioned briefly or skipped over. And there are many others here, in fact. So there are many different protocols used at the physical and data link layer. Above IP, we've just mentioned there's something called TCP, which is a transport protocol. There are some other transport protocols, including UDP. And above that, we have all our application-specific protocols for web browsing, for email, network management, domain names, and many others in here. Instant messaging, voice, video transfer, and so on. We can sometimes think of IP as at the center of the stack, and it's considered perhaps the most important because everything above here eventually makes use of IP. And IP works or operates over many different LAN and WAN technologies. There are some small extensions or protocols that support IP. ICMP will mention ARP and some specific routing protocols. This is one of our longer topics, or perhaps the last long topic for this semester. So what we'll do today is just go through how IP works, some basics, finish with an example today, and tomorrow we'll get on to some of the details of how addresses and so on work. And by the end of tomorrow and early next week, it should all come together and you'll understand how IP fits within the internet. When we want to send data from our source computer to our destination computer, in the internet we create what's called an IP datagram. Some packet or frame, but we refer to it as a datagram or an IP datagram. As we've seen with many other protocols, it has a header and some data. The structure of that datagram is shown here. The way to read this diagram is that you read it row by row. So this is one row, the next row, and so on. So we think this is the header, these rows. After the header, we have the data that we want to send. And in each row, we have 32 bits, or 4 bytes. So if we number the bits in the header, bit 0, if we start at 0, up to bit 31. That is 32 bits in the first row, followed by 32 bits in the second row, and so on. It's a common way to write down the structure of a particular header. Of course, a packet is simply a sequence of bits, but to visualize what that packet looks like, or a datagram looks like, we often use these types of diagrams or tables. Inside the header, there are different pieces of information, and that's what's listed here. These are the fields of the header. We'll go through and describe the most important ones. And we can see the length of each field. The first 4 bits of an IP datagram is some 4-bit number that indicates the version of IP we're using. We're talking only about version 4, so of those 4 bits, it will always be the binary value of 4. 0, 1, 0, 0. So that's all the value of the version field is, the version of the protocol we're using. The next field is 4 bits in length. The next one is 6 bits, 2 bits, and so on. Some of them, all right, let's go through them. H length, and they're described on the next slide. H length is the length of the header. We'll see that the header by default has a size of 20 bytes. But we can add some optional header fields. So in fact, it can be larger than 20 bytes. Therefore, we specify the length in this field. Diffserv and ECN are used for only very special cases for providing in networks that can provide priority. So some extensions of IP to provide priority, quality of service, are used in these two. We normally do not use them, or will not describe them any further. Total length is a 16-bit number that indicates the total length of the datagram. we have the header plus some variable size of data. This indicates where does the data finish by saying, okay, if the total length is 1000, that it indicates how many bytes of data we have in here. That is, the size of the header plus the data equals the total length. Identification is just a sequence number, so it's a sequence number included inside the header. So if I send 2 IP datagrams, they'll have different IDs, different sequence numbers. Flags are 1-bit values, so with 1 bit they're either on or off. The flag is either 1, it's on, or 0, it's off, to indicate some functionality. And we'll see that the flags of interest are used for the process of fragmentation and reassembly. We'll cover that in some depth where we need to break IP datagrams into smaller IP datagrams. We need to fragment them. So some of the flags and the fragment offset are used for that purpose. We'll cover that later. Time to live, we know what that is. That's like a hop limit. It limits the time for this datagram to live in the network. And the basic way it works is that if we set the initial value to be 5 for the time to live when we send it, and we send it to a router, the router will decrease it to 4, and this one will decrease it to 3, and then we'll send it on, and it's received. If it gets to 0, then a router will not send it on. We saw this concept in flooding where we use a hop limit. If the hop limit gets to 0, we do not send anymore. That's the same concept here with the time to live field. The protocol field indicates what is the content of the data. What protocol is being used above IP. So our application generates data, eventually sends to the transport layer, and one of the transport layer protocols sends the data to IP. The protocol field indicates which transport layer sends to IP. The different transport protocols have numbers identifying them. TCP is the number 6, UDP is the number 17. So if TCP puts some data into our IP datagram, the protocol field will have the value 6, just to indicate that the protocol, the data we're carrying is from the protocol TCP. We have a checksum used for error detection, but note this is just error detection across the header, not the data. Error detection is if there are any bits that have changed from when it was sent to when it's received, we will use this to check whether any of them have changed, if there are any errors in the header only. So if something goes wrong in the transmission and there's an error in the header, we can use this to detect that at the receiver, but not errors in the data. The next two are the addresses. These are the addresses of the source device and the destination device. And the format is that there are 32-bit addresses, IP addresses of the source and destination. We'll spend some time going through the precise structure of IP addresses in the end of this topic. Note that the source address is the original source of the datagram, and the destination is the final destination. In our example here, we could see that we send an IP datagram from our source to a router, to the destination. The source address is this device, the destination is this device, even as it passes through the routers. Normally they do not change, and only in very exceptional circumstances would they change. The source is the original source, the destination the final destination. We can optionally have some extra fields in the header, but we'll not explain what they're used for. You'd have to look at some of the details of IP to cover them. And then we include our data. And the data may be a variable size. The maximum size of the header plus data is 65,656 bytes. It's determined by the total length field. We have a 16-bit number. The typical size of the header is 20 bytes. So if I give you a question that it's about calculating how long it takes to transmit an IP datagram, if I give you this diagram, you would know, okay, the IP header is 20 bytes. Assume that there are no options, because we will not cover how they are used, the options. So we assume that doesn't exist, and then we have the data. So 20 byte header plus data is the size, the typical size of an IP datagram. Those fields are described in a little bit more depth, listed there. We'll see the most important ones in use through our examples. What does IP do? IP, we said before, is a connectionless internet-working protocol. Well, what's that mean? Let's compare it to a connection-oriented internet-working protocol first to explain what it means. If we had a connection-oriented protocol, then we establish a connection between source and destination before we send data. This source A1 wants to send data to this destination B3. If we were using a connection-oriented protocol, we'd send a special message saying, I want to send data to you. This one would respond saying, yes, you can send data, and then we would send the data. We've seen this concept in virtual circuit packet switching. We set up a connection, we transfer the data, and then we terminate that connection. We don't use that in IP. IP uses the other approach of connectionless. There's no connection. And that's the concept we saw with datagram packet switching. We want to send data from A1 to B3, create a datagram and send it. No concept of setting up a connection. As a result, datagrams are treated independently. I send my first datagram, it may go across one path. I send my next datagram, it may go via a different path, and it may be treated differently at the individual routers. So this is the case with IP, connectionless internetworking. They both have advantages and disadvantages. The good thing about the internet protocol and connectionless internetworking is that it can deal with different variations of what our applications require. If my application needs to set up a connection to transfer the data, it can do so, still using a connectionless internetworking protocol. If my application doesn't want to set up a connection, just wants to send data, then it's very efficient to use IP or a connectionless internetworking protocol. If we use connection-oriented internetworking and my application didn't need to set up a connection, we still need to set one up with our internetworking protocol. So connectionless seems to be the more flexible or adaptable depending on, or to be able to support many different types of applications. So low overhead, we don't have to set up a connection. So that was the design decision when people designed the internet protocol. Within our devices in the network, we can distinguish between two different types, hosts and routers. So in my example diagram here, I said this is an end user station. Someone uses this device, say a PC. This is a host. This is a host. These two are routers. Let's look at the differences between the types of devices. A host, an end user device or a station, normally uses only one interface at a time. My laptop would be a host on the internet. I'm currently connected to the wireless of SIT, the wireless LAN. So I'm using my wireless LAN interface. Normally on your end user station you only use one interface at a time. You can use more than one, but in practice today most people just use one. That is, I'm either using my wireless interface or my wired LAN interface. That's common with most hosts. In fact, my laptop has a Bluetooth interface, wireless LAN, and an Ethernet wired LAN interface. It has three interfaces, but normally I'm only transferring data across one at a time. There are special cases where we can transfer across two. A router will normally have two or more interfaces and maybe using them at the same time. Why does it have more than one interface? Because a router connects subnetworks together. So a router, we can think, has at least two cables plugged into it. One for this LAN and one for this wide area network. And in fact it may attach to more than two subnets. So a router usually has two or more interfaces and usually uses them at the same time. A host does not forward IP datagrams. By forwarding we mean to receive and send on. That's the process of forwarding. A router does forward IP datagrams. And if there's one way to distinguish between a host and a router in this course, that's it. If a device forwards IP datagrams, it's classified as a router. If it does not, it's classified as a host. Here's our host. It sends an IP datagram. So it's the originating source of the IP datagram. It sends to a router. The router forwards that onto the next router, which forwards that onto the eventual destination. So the routers forward the datagram. This host did not forward the datagram, it created it and sent. This host did not forward, it received and consumed the data in that datagram. So that's how we distinguish between a host and a router, whether or not they forward datagrams. Is my laptop a host or a router? Simple question, common in quizzes this week. Quizzes every week from now on, we've only got 3 weeks left. Is my laptop a host or a router? My laptop. Yeah, host. Can it be a router? It can be a router. In fact, we'll see mostly next semester in our lab, that the difference to turn a host into a router is usually just a software difference. It can be done inside the operating system to turn a host to a router, to make it not forward datagrams to forwarding datagrams. It's usually just some software configuration. But in practice, your laptop or PC usually acts as a host. Hosts are either a source or a destination. This host is a source, this one is a destination. Routers can act as sources and destinations, but not very often. This router could be a source of a datagram. It could originate a datagram and send to here. That's possible, but it's mainly used for management reasons. If I want to change the configuration of this router, maybe I would connect to it and this would be a destination and a source. But in most cases, we can think of a host as either a source or destination, and a router simply forwards datagrams. It doesn't originate, or they do not originate from the router, nor end at the router. They can in practice, but not so often. IP routing is the process of finding the best path from source to destination, from here to here. We know that. the general concept of routing. Forwarding is the process of getting the data from here to here. Routing, create the routing tables in the individual devices. We'll see that each host and router has a routing table. So in a particular network, we can create the routing tables which contain information about the least cost path through the network. Forwarding, once the routing tables are created, when I have a datagram to send, I will use those routing tables to send to the destination. So we usually distinguish between the two. Let's go through an example to illustrate some of those concepts. Actually, before the example, we may go through something else. This is just another example network where we have multiple routers, multiple subnets, and a source and a destination, similar to here, but I have only 2 routers. We'll go through this one in a moment, but I just want to explain one more concept to help in that example. IP routing. So there's the concept of routing and forwarding. Routing in the internet, or within the internet protocol, there's no specific routing protocol. That is, within the internet, you can choose between many different routing protocols. You don't have to use one specific routing protocol. And there are many available. And those routing protocols may use different metrics, different routing strategies, different algorithms for calculating least cost routes and so on. So we cover them, or the differences between routing, in our routing topic. And also we covered in our routing topic what happens in adaptive routing. Routing protocols calculate the least cost paths and store that information in routing tables. And then the Internet Protocol, IP, uses the information in the routing tables to forward the datagrams. So we saw how to create routing tables in our previous, or one of our previous topics. Let's look at an example. Example routing table to illustrate some concepts. I'm just creating an internet. It has 4 subnets connected in a simple configuration with 3 routers, and each subnet has some hosts attached to it. Let's give it 3 hosts each. H1 through to H12, host 1 through to host 12. Let's quickly create some routing tables. And in our network, both hosts and routers have routing tables. But we'll see that there are some simplifications, or there's some strategies to make the management of those routing tables easier. We've already seen one strategy, that is to store only the next hop in the route, not the entire path. For example, let's draw the routing table for R1, or at least start drawing it. A routing table stores for some destination what is the next node in the path. This is the routing table for R1. The first strategy listed here, storing next hop routes, we already know about. That is, we don't store the entire path from R1 to every destination. We just store the destination and the next node in the path. That makes the routing table simpler to manage. It's smaller, easier to update. So some of the paths, let's look at our hosts as destinations. To reach H1, what's the next hop in the path? Direct. That is direct to H1. Note that everything attached to the same subnet we can send direct. It doesn't matter whether it's a star topology, whatever the topology in here is, we don't show that. We just say that they're attached somehow via the LAN technology here. So we can say, okay, to reach H1, the next node is H1. We'd say that for H2 and H3. In fact, R1, router 1, is attached to this subnet and it has direct connections to H5 or H4, H5 and H6 as well. Because R1 is attached to these two subnets, so whoever is also attached to these two subnets, R1 has direct connections to. That is, they're the next node on the path, H1 to H1 and so on. Let's try some of the others, a bit more interesting. To reach H7, to reach host 7, if we're at R1, we should send to R2. That is the next node in the path to reach H7. I'm going to run out of space. For H8, it's the same. For R1, to reach the destination host 8, send to R2. That's the shortest path. In fact, that's the only path in this simple network. And H9, R2. And in fact, I'll just keep drawing here because I've run out of space. I would need these three, H4, H5 and H6, as well as H10, 11 and 12. To reach H10, what's the next node? R2 still. If we're at R1, we want to reach this host, send to R2. Same with H11 and H12. And let's be complete, I'll do these three as well. H4, H5, H6. That would be our routing table for router R1. We store the next node in the path, not the entire path. That's the first way to make the routing table simpler. But there are two other approaches we can use. Notice that if I have, instead of 3 hosts on this subnet, I have 300 hosts on this subnet. Okay? So many more hosts on this subnet. My routing table would have to have another almost 300 more rows in here. That is, to reach well, let's focus on the N subnet. We can go up. If there are not just 3 hosts here, but 300, then to reach H10, send to R2. To reach H11, send to R2. To reach H12, send to R2. If there were more hosts, to reach H13, send to R2. 14, R2. To reach host 100, send to R2, and so on. the more hosts we would need an individual entry in our routing table. How many hosts in the internet? How many hosts in the internet? More than 1,000? How many computers? Uncountable. All right, that's okay answer. That is too many that we can count. Possibly billions. Here, in our internet, router R1 needs a row for every host. If we looked at the entire internet, we'd need billions of rows. It's just not manageable, and we need to update them. The first simplification is to notice to reach any host on this subnet, send to R2. So we can simplify by giving our subnets names. Let's call this net 1, subnet 1, net 2, net 3, and net 4. Now, from R1's perspective, we can say to reach any host on net 4, whether it's H10, H11, H12, H300, send to R2. That is, we could replace these 3 rows with 1 row. To reach anyone on net 4, send to R2. So now this 1 row in our routing table can be used to reach any host on that subnet. And in fact, we can do it with the other 3 subnets as well. To reach any of these 3 hosts, we send to R2. That was these 3, H7, H8, H9. So instead we say to reach any host on net 3, send to R2. So that's cut. In this simple example, we've removed 4 rows from our routing table. If we had 100 hosts here, we would have removed 99 rows from our routing table from that case. So the more hosts, this becomes very simple. We just have 1 row, 1 entry in our routing table for the entire subnet. This is called network-specific routing, or as we make use of network-specific routing. The router doesn't care which host it wants to reach. It just wants to get the datagram to that specific network. If router 1 can deliver the datagram to router 2 can deliver to router 3, then router 3 can deliver to the individual host. Router 3 knows the individual hosts. These routers do not need to know about H10, 11 or 12. They just need to know, it just needs to know that to reach network 4, send to R2. Simplifies routing and makes it manageable within a large network. Another thing that we can do, or will often do, is in these cases we said from R1 to reach H1 we send direct to H1. Okay, R1 to H1 direct. Sometimes in the routing table we would, instead of writing send to H1, you'll often see an example which says, okay, just send direct. We use a special entry. From router R1 to reach any host on a subnet that we're attached to, send direct to that host, using the technology of that LAN or wide area network. And the same here, to reach H4, H5 and H6, send direct to that host. That is, they are the destination. If we do that, we can of course simplify again, because we can say to reach any host on network net 1, for R1 to reach any host on this network, use your LAN or wide area network technology to send direct to them. Maybe this is a star-based network. Maybe there's a switch in the middle, there's a link to the switch, and each of these have links to the switch. And it uses Ethernet. It is 802.3 that we covered last week. So when router 1 has a datagram and it wants to send any host on this network, it just uses Ethernet to deliver to that host. It uses the underlying technology to do that. From the routing table's perspective, it simply says, okay, to reach anyone on that network, send direct to them using your own technology. Router 1 can send to anyone on this network, and same on network 2. So from the routing perspective, we've simplified our routing tables to just 4 entries. To reach network 1, send direct to the host. To reach anyone on network 2, send direct. To reach any host on network 3, send to R2. And then R2 will send direct. And to reach any host on network 4, send to R2. And R2 should send to R3, and then R3 would send direct. So this takes advantage of that we do network-specific routing. Next simplification, default routes. Let's say instead of just, we've got R1, R2, R3, let's say it continues, R4, R5, R6, and R100, and so on. From R1's perspective, we would need another entry for each of these subnets here, for net 5, net 6, net 7, net 100. We'd need rows for each of them. But we can simplify again. From R1's perspective, to reach network 1, send direct. To reach network 2, send direct. To reach any other network 3, 4, 5, 6, 7, 8, send to R2. So we could say by default, send to R2. To reach your local network, send direct. Otherwise, send to R2, a default route. And therefore our table becomes, I'll combine it all together. We won't need this. To reach any host on network 1, send direct. To reach any host on network 2, send direct. To reach any other host in our internet, I'll use star as a wildcard to indicate any other value. To reach any other value, send to R2. That is, if I want to reach someone on network 3, we do some matching. It's not network 1, it's not network 2, therefore it matches this value, which can be any other value. So if I want to reach network 3, send to R2. If I want to reach network 4, send to R2. If I want to reach network 1 million, send to R2. So now this single entry covers any other network in the internet. So that's very useful if we have hundreds of thousands of networks. We've reduced our simple table from originally, I think, 12 rows down to 3 rows. In the larger internet, using these concepts makes a routing table manageable. They were examples of network-specific routing and using default routes. Of course, that's just for R1. You'll go home tonight and create a routing table for R2 and R3. And Here's a simple one. In the last 2 minutes, draw a routing table for H3. What's the routing table for host H3? Routing table. What's the first entry? H3, host 3 is on network 1. Destination, the simplest, to reach anyone on the same network, remember this is network 1, to reach anyone on net 1, send direct. That is, we're on the same network as them. To reach anyone else in the world, star, send to R1. That's it. Here, if I want to reach someone on this subnet, I can send direct to them. I don't need to send to a router. If I want to reach anyone out here, I will send to R1. And then R1 will look in its routing table. If the destination is H10, then will match this row. It will send to R2, and R2 would use its routing table, and so on, until we reach the destination. So store just the next hop in the routing path. Store paths to networks, not to individual hosts, and use default routes. 3 ways to simplify the routing table management. Tomorrow we'll continue with our example and continue with our explanation of IP and go through this diagram and move on with IP. Enough for today.